So this, I think it's interesting to explore if with this kind of non-covalent interactions attaching adequate ions to the surface, you could look for a way of doing very simple biomimetic electrocatalysis. And I will just come to the last experiments we have, or I would say, actually, we should say the first experiments we have been doing in Aberdeen. This is work from a fourth-year student. I am really happy with him because he's fourth year, never did any electrochemistry at all, and is doing excellent experiments, beautiful ones. So here, I had something very strange with this pH effect when we did the experiment in potassium hydroxide. And it was that the region here, before hydrogen, or let's say hydrogen adsorption, the formation of the CNH group was shifted very much in the negative direction. So obviously, then I told him, make cyclic voltammograms of cyanide-modified platinum 111 at different pHs. And what we see is this behavior that we see here. So this is pH 1, pH 4, pH 7, pH 10, and pH 13. And obviously, when we move from pH 1 to other pHs, we're introducing some cation. In this case, it's sodium. So we were expecting, due to the presence of a cation, a shift of this region to more negative potentials. And this is what we have. But actually, this shift is much higher than we expected. Because if you look, for example, at the case of pH 10 and pH 7, this is sodium in the solution. At pH 7, we have more sodium than at pH 10, but still at pH 10, so this is just a graph from the student. This makes no sense. So this is just adjusted means that he has converted it to the reversible hydrogen electrode. And this is the potential as measured versus a silver chloride. So here you would expect a 60, you would expect a 60 millivolt per pH unit shift in the negative direction. But we have more than that. We have 90 millivolts per pH unit. And obviously, the presence of sodium is accounting for that. But it's not only sodium. Because as I say, here we have more sodium than here. But still, when we go from 7 to 10, the potential shifts negatively. So I don't know what it is, what's happening here. Initially, I thought that we could be looking at the coupled proton-electron transfer. But then I realized that this is just nonsense, because what we have to do, what we are doing here is, again, changing delta G of the process. This means that you are changing either the initial state or the final state. And even if with the coupled proton and electron, we still have the same initial state and the final state. So this explanation makes no sense. I don't know what's happening there, but it's something very, very interesting that we are provoking a super-Nestian shift of this peak when we change the pH. And well, this is now work for the future, and I hope that next time I come here, I can give you an explanation to this, hopefully. I don't know. Well, now before finishing, there are some conclusions here. Well, I don't want to bore you just reading them. So while I just speak, I talk a lot. If you are interested, you can read them. And otherwise, I just go to the next slide. And first of all, I want to thank all the people that have collaborated in this work. First of all, people who put the money, not much actually, that's why I'm not there anymore. But also people who collaborated with us, Argonne National Laboratory, who collaborated in the work with oxygen reduction reaction, people at the National University of Córdoba in Argentina, Ezequiel Leiva, who did a lot of calculations, and most important of all, the people who really did the work. So Maria did the work with oxygen reduction reaction and the effect of sodium on the cyclic voltammetry of cyanide-modified platinum 101 in acidic media. Gemma, you will know her soon because I think she is going to come here. And she did very, very precise work, beautiful work, this part of the effect of the cations on the adsorption of sulfate. And this is the work that we still have to publish. So this will be her last article during her PhD period with me, even though this was not part of her PhD. And Chris Wilde, who is the student who is working with this thing now, and hopefully he will go on working on it during summer. And just, well, just probably you see, sometimes there is sun in Scotland, not very frequent, but sometimes you have it. This is King's College, which is the oldest building in the university. The university was founded 1495. It's the 5th oldest university in the UK, the 3rd oldest university in Scotland. They are very proud of that. I have to be proud of that now too, since I am part of them. And, well, Aberdeen is not so beautiful as most of us cities in Spain. There are much more beautiful cities in Spain than in Aberdeen, but you can see some beautiful things there. And if anyone feels interesting to come there, just remember it's not only for Highlanders. You can see some Latin people there too. And there are quite a lot of Brazilian guys there. And I am surprised. Well, I should say it's sad to say that there are a lot of Spanish people who have moved there too. Not only in Aberdeen, in the whole UK, but in Aberdeen there are quite several of them, some lecturers. And well, if any one of you is interested in coming there, you will be welcome. Thank you very much for your attention.
I was surprised that when you look at the vibrational frequency of this CN, it was shifting with potential. And then when you said that the hydrogen was bound to CN, forming CNH, there was a change in slope.
Yep.
Would it be a jump in frequency because you break a triple bond and make a single bond with hydrogen?
I don't think so. I don't think so because this would be true if you were going suddenly from 3 CN molecules to 3 CNH. But we are actually not having that. We are having a gradual addition. Actually, we are not making. Protons are behaving very similar to the cations. So protons are going to the cavities, and actually protons are forming, we believe, and that's what the calculations say too, they are forming a kind of delocalized bond with several cyanides around them. And actually, if you look at the voltammograms, this will be enough. If you look at this red voltammogram, from here to here you have 600 millivolts. So here you have a very small amount of hydrogen, so 1 hydrogen per 10 CN groups. And here we have nearly 1 hydrogen, something like 1 hydrogen per 2 CN groups. So you never come to create a full CNH monolayer. You have something like CNXH, and this covers the whole thing. Actually, this was the origin of these experiments, because I thought, and there were some old results in the literature from the 80s, I thought that the whole surface could behave collectively as a polyprotic acid. And I was actually interested in looking at the hydrogen charge as a function of pH, and I was expecting to have some kind of titration curve, which then I realized which is absolutely absurd, because this would mean that I would be changing delta G of adsorption. But meanwhile, while I was realizing that the idea was completely stupid, the student had already had time to do the experiments, and we found this remarkable behavior, which is it's as remarkable as it would have been if I had found what I was thinking of, which I realized could not be true. But anyway, the whole thing is that the surface, the cyanide layer is behaving collectively, and you are not bonding 1 hydrogen atom to 1 CN. So every time you transfer a proton to the surface and you create CNH, you are actually transferring it to the whole ad layer, not to a single CNH group. And that's why it should be gradual, the change. Actually, this infrared experiment, we have to repeat it, but because what we did was a very rough experiment. We were changing the potential in 2 big gaps. Actually, what we should do is do this experiment at very small potential intervals. And I am pretty sure that if we do that experiment at very small potential intervals, we'd actually see here a curve rather than a straight line. So I do think that we have a straight line here where nothing is changing, and which is the typical Stark effect. But I am pretty sure that here, the frequency should change gradually in a curve. And that we are seeing a straight line simply because we are using very, very big potential steps. But we have to repeat this experiment because I am pretty sure that this must be gradual, just as the hydrogen absorption is gradual too.
When you modify the surface with cyanide on the hydrogen region, the current and probably the charge is kept constant. But on the OH region, when you increase the sodium concentration, you lost this reverse.
Honestly, we've got no idea what's going on in the so-called OH region in this cyanide modified surface. No idea what it is. And it behaves very, very strangely. I don't know if I have the results here. So actually, we don't know. We call it OH adsorption, but we don't know what it is. And when we add cations, it behaves very strangely. And this is something that is keeping me completely puzzled and has kept me puzzled for now 5 years, maybe more. I still don't understand what's going on there. Yeah, you don't see it here. I think you see it here. If you look at this blue line, when we have this high concentration, no, it is not this here. Let me look. It must be somewhere. Well, there is some cases. Usually, you see this peak on the positive, in the positive sweep is slightly more positive than the peak on the negative sweep. I don't remember if it was with sodium or with potassium. I think it was with potassium. When there is a concentration of potassium in which the positive peak appears more negative than the reduction peak. I have no idea what it could be.
Is the profile stable?
No. Well, with time it is. It does not change at all. It does not change at all. This is completely always the same. Does not change. But I have never seen something like that. So you just go increasing potassium, and initially you have the normal behavior, but there comes a potassium concentration in with the peaks look something like this. So
there's more charging of the reduction than
it's more or less, yeah, absolutely. So this is absolutely puzzling. I've got no idea what's going on there. And at this moment, we haven't got information. So obviously, one thing that we have to do is doing infrared spectroscopy. We've got infrared in acidic media, but we haven't done any infrared in the presence of cations. And I hope that doing infrared will tell us something about what's going on there. Because, as I said at the beginning, now we only have current and potential. And you can do many beautiful things with current and potential, but you can't ask them more than they can tell you. And they cannot tell us what's the chemical nature of the things going there. And no idea what it is. But it's really very, very interesting. And it's remarkable that we have very, very strange behavior.
The last experiment that you were doing with the fourth year student, are you planning to change the design?
Yes. Actually, my initial idea was to do the experiment with potassium, because we know that potassium has a bigger effect than sodium. But we use sodium because the solubility of potassium perchlorate is much lower. And we wanted to make buffers, and initially we wanted to keep the cation concentration constant. But for some reason, actually, without thinking about that, I told him, yeah, we will make experiments keeping the cation concentration constant, but first do it, just don't care about that, and then we go far, just to have a bigger set of data. And then it was good to do that, because we could see that in some cases with higher concentration, you still have a more positive potential for hydrogen adsorption than at a lower concentration, but a higher pH, which is really remarkable. So yes, the answer is yes, we are going to use other cations, but in any case, what next step to do is to change the pH, but add cations intentionally so that we keep the cation concentration constant. There is another difficulty in these experiments, because if you do that, obviously by adding a cation, you also have to add an anion. You cannot separate anions from cations. Nature is neutral. This means that we are going to change the ionic strength of the solution too. And we don't know if this will have an additional effect or not. So actually the problem is quite difficult from an experimental point of view to find experimental conditions in which you know that only one of the things that you are changing is having an effect and not 2 or 3 of them together. I cannot hear you, sorry.
The absorption of metal ions on surface of carbon nanotubes. You have some slides about that.
Are you meaning
yes.
This?
Yes. Where we can find the application for these kind of concepts?
This has no application at all. This is fundamental science. just having fun and learning.
It's a very difficult thing to separate the single wall carbon nanotubes from the multi-wall carbon nanotubes. Whenever you
I cannot hear. I will come to you. Yeah, tell me.
Whenever you prepare single wall carbon, try to prepare carbon nanotubes, there is always problem that you cannot separate carbon nanotubes single wall from the multi-wall carbon nanotubes. You have a junction of both the carbon nanotubes. So these kind of applications we can apply for both kind of carbon nanotubes, or whether we need to specify first that we have a carbon nanotube this field like single wall only, and then we apply the metal resorptions to the surface.
My answer is I have no idea. I cannot give you a yes or a no because I'm not familiar at all with this kind of problem. So no idea if you could apply this. Sorry.
When you change the ion concentration, the cation concentration of the solution, you change the screening of the electric field at the interface. So you change the capacitance basically. Now that should shift the amount of charge on the surface. So is there a change in the zero charge point with the basically the ionic strength of the solution?
Very good question.
And how would that have an effect?
Very good question. We thought of trying to measure the potential of zero charge here, but I don't see a way to do it. So obviously, Chapman is not going to work, and zero charge displacement is not going to work too. So we actually did some zero charge displacement. Actually, zero charge displacement was the first experiment that we did with this system. And the problem is that zero charge displacement is very good to measure the potential of zero charge if the charge density of your platinum surface is much bigger than the charge density on your CO-covered platinum surface. Because what you are doing is measuring the difference in charge between the CO-covered and the CO-free surface. In this case, this is not true. So one thing that we saw when we did zero charge displacement experiments is that the charge displaced is very small. And this means that probably the charge density is very similar before and after. So you cannot use that to measure the potential. I don't know how to do that. No idea. But coming to your comment about the capacity, we don't see a big change in the capacity. If you look at the double layer region here, it changes a little bit. It's smaller in the presence of the cations, but not very much. So it's not very significant. So I don't think this is a very relevant effect that we are having there. And we see the same again in the last experiments that Chris has done. In the last experiments, we see again that the double layer region remains more or less the same. So it doesn't seem to be a big change in capacitance. Would be interesting. We have talked about that with Ernesto. We already talked about that last time I came, and we have talked about that now again. About it would be interesting to make some impedance here, not only for this but also for other reasons. But we haven't done anything yet.